Hello, everybody, and welcome to chapter number 2. This is Professor Algarra, and I will develop all the information related with chapter number 2. This chapter has a lot of information about energy, energy transfer, and finally, general energy analysis. But before I start the chapter, I want to remember what we covered in chapter number 1. Remember a lot of important definitions such as what thermodynamics is, pressure, temperature, state posture. It's very important that you read the chapter in order to move into chapter number 1. Otherwise, it's going to be very hard for you to understand every chapter. Okay, so just keep that in mind. Read every chapter before you move to the next one. And if you have doubts, like I said, you're more than welcome to go to my office hours so we can clear those doubts. Okay, so we're ready now. Chapter number 2 is energy analysis. So as you know, energy, it's an important part of most aspects of daily life. The quality of life and even its sustenance depends on the ability of energy. Therefore, it is important to have a good understanding of the sources of energy, the conversion of energy from one form to another, and the ramifications of these conversions. Energy would exist in numerous forms, such as thermal, mechanical, electric, chemical, and nuclear. Even mass can be considered as a form of energy. It's very important that we know that energy can be transferred in two different forms, heat and work. That will be developed later on the chapter. And I just wanted to give you an insight of what the chapter will look like. So moving, we have the form of energy. Like I said, it will exist in different forms. Okay. In thermodynamics, we don't deal with the absolute value of energy. We deal instead with the change of the total energy with respect to a convenient reference point. That means that we can assign a zero total value of energy as a reference point and calculate the change in energy with respect to that point. Okay? So forms of energy are very important. We have pretty much three forms of energy. We have macroscopic form of energy, microscopic, and then internal energy. And to give you a little bit of information, the macroscopic form of energy, those are the ones that depends of a reference frame, such as kinetic and potential energy. And then we have the microscopic, which pretty much are the ones related with the molecular structure of the system and the degree of the molecular activity. The internal energy will be the sum of all those energy. So if we have, okay, the macroscopic will be pretty much potential energy and kinetic energy. And this one will have an equation and another equation. The micro form of energy will be pretty much the sum of all. No, it will be all of the energy that are related to the molecular structure. And finally, internal energy, which is U, will be the sum of all micro energy. Keep that in mind. Moving to the next slide, we're going to start pretty much not defining because this is much more related to physics than it is with thermodynamics, but I just wanted to remember what kinetic energy and potential energy are. So pretty much those are the system, those a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential. Everybody's familiar with this. Okay, kinetic energy is the energy that a system possesses as a result of its motion relative to some reference frame. Okay, kinetic energy is the energy of the movement. When something is moving, it's generating kinetic energy. I've included a video about potential and kinetic energy here on Blackboard, so make sure you watch those videos. Potential energy is the energy that a system possesses as a result of its elevation in a gravitational field, and it is expressed with this equation. Some people will remember potential energy as mgh. Okay, So mgh and mgz will be exactly the same thing. What is changing is just the letter that they use um, to refer to the elevation or height, okay, which is h and z. Okay, so moving to the next one, we have the microscopic forms of energy. Pretty much are those related to the molecular structure of the system and the degree of the molecular activity. And they are independent of the outside reference frames. The sum of all microscopic forms of energy is called internal energy of a system. And that, guys, is what we need, okay? The internal energy. That's the inside information that we need to get in order to move into the analysis. So don't worry, I know that right now, as you're watching the video, you will have like microscopic forms of energy. I want to know what they are. I want to imagine those chemical reactions. But just think about it. When you're talking about mechanical movements, it's super simple for you to imagine how a wheel would turn or how a system will move from point A to point B because you can visualize that in your head. When you're talking about chemical reactions, it's pretty different and a lot harder because you need to imagine that chemical reaction, and sometimes that could be a challenge. Okay, but we don't worry about those chemical reactions. We worry about the sum of all of them, and we call that internal energy. With that being said, we're going to call total energy of a system. The magnetic, kinetic, surface tensions, are significant in some specialized cases only and are usually ignored sometimes, okay? When we talk about a system that has a lot of different forms of energy, that's what we need to calculate. How much energy do I have at a state number n, and how much energy do I have at a state number x, and then I can compare them both and then get the change of that energy. Sorry if I speak a little bit fast. Okay, so I just want to clarify, I'm using these presentations so you can know a little bit about the information, but remember, you need to read the book. Guys, that's the key with thermodynamics. You need to read the book in order to fully understand the terms and definitions. Okay, so we have the total energy of the system will be equal to internal energy, then kinetic energy and potential energy. We know that, internal energy is just internal energy as we know, and kinetic energy will be equal to mass that multiplies v squared over 2. V is the velocity, and potential energy will be mgz or mgh, that will depend. There is something important right here, which is a unit. The unit is kilojoules for energy, and you have to remember that because units, it's usually what will take you to a wrong answer if you don't know exactly what you're playing with or exactly what you have in your hands in order to develop the exercises. So energy will always be given in that unit, which is kilojoules, and then we have the little e. Okay, the little e would be pretty much the energy per unit mass. Okay, and it's super simple. So the little e will be equals to capital E over mass. Okay, so the energy of a unit mass basics will be equals to the total energy of the system over the mass. I just want you to remember that, and that will develop later on. Something super important is the mass flow rate. Okay, mass flow rate, it's just an equation. And I want you to know that it's just an equation, especially right now because you're getting introduced to a lot of things. And I want you to look at it as an equation. Okay, in engineering, it's usually easier to understand, perfect cases, ideal cases, so we can understand what is not so ideal or something that is more adapt to the reality. But we need to know exactly how it will work perfectly so we can deal with mistakes and things like that. So I just let's read this through. Mass and energy flow rates associated with a flow of steam in a pipe of inner diameter d with an average velocity, and then they tell you the average velocity. And finally, this is equation they developed. So mass flow rate, they said that is equals to density and cross-sectional area and then the average velocity, okay? But I don't like when I just been given with an equation and I want to know at least where the equation is coming from, and I'm going to try to do that right now. Okay, so we know pretty much from the book, when you read it, you will see that the mass flow rate it's equals to density times, okay, volume flow rate. I know that my volume flow rate it's equals to over time. That's pretty much what it is. What is the volume equals to? Volume it's equals to the cross-sectional area times distance over t. How so, professor? Okay, let's say you have a cube of water. This guy right here is the cross-sectional area. The distance right here, I will call it distance. And that's why your volume is equals to the cross-sectional area times the distance. What would be, I want you to know what distance over t will look like. I want you to know what distance over t will be. What is distance over time? Do you remember anything? I mean, if you were in a classroom with me, I would ask that question. But distance over time, it's what? Velocity, right? Equals to distance over time. If you remember the units, meters per second. You remember that? So what happened in a pipe? I have a pipe right here going through a fluid. This guy right here is the cross-sectional area. And I'm going to imagine a little cylinder that goes through that pipe, and this little cylinder will have the distance d. That's what I'm getting this from. Okay? But inside of the pipe, the velocity will pretty much behave like this. Okay? You're going to have a higher velocity in the middle of the pipe. So in engineering, when we are developing equations, we can probably standardize some definitions in order to develop the equations at no cost in accuracy. Okay, and that's what I'm going to do right now. So if I have B1 and B2 and B3 and B4, at some time it's kind of hard to integrate those values. So instead of going that, we're going to go to a midpoint right here, and I'm going to call that an average velocity. Okay, so I can have an average of those velocities. And now, or therefore, my mass flow rate will be equals to, like I said, I'm sorry, before I move to that, so we were velocity is equals to distance over time. So instead of calculating velocity 2, velocity 3, or 4, or 3, we're going to call that velocity average. And that will be equals to distance over time. So the mass flow rate at the end will be mass flow rate is equals to density, right here, density, and then volume flow rate, which is not more than cross-sectional area, and times velocity average. And you can call velocity average like this. It will be different from one book to another, but this is the equation, the final equation. Let me just go back to you can see it. This was the equation we were developing, okay? Density, cross-sectional area, and average velocity. All right, I hope you understood this, but ultimately, guys, we only need to know the equation, okay? That equation, it's important one. It's very important, okay? So save it for your exercises. Why it's so important, you might ask. I'm just, talking to myself because I remember all the questions that usually students will ask in a classroom. So the energy flow rate, or anything that has a flow rate, it needs to be calculated in order to know the behavior of some engineering devices. In order to get that, and so we just define energy and we just define the mass flow rate. So I'm gonna define something that is called the energy flow rate. Super simple. Energy flow rate, which is the E dot, will be equals to the E that you calculated before that we defined multiplied by the mass flow rate. Okay? and this one has a unit of kilojoules per second. Okay, the mass flow rate will be kilograms per second. Okay, the amount of mass that goes in a some time, T1, T2, T3. Those two, very important. Okay, moving to the next slide. Are defining the forms of energy. And I just want to give you a small introduction about it, okay? Even though I know in chapter number 5, 6, and 7, we're going to be developing each one of those forms, and you're going to see the applications of each one of those forms of energy. Okay, so mechanical energy, the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device, such as, an ideal turbine, compressor. We're going to be defining mechanical components, so don't worry. Kinetic and potential energy, the familiar form of energy, the familiar forms of mechanical energy. We have 3 forms right here. Something that is called the mechanical energy of a flowing fluid per unit mass. So we have this guy right here. We don't know what that is. We have this guy and we have this guy. So this guy right here, it's kinetic energy, and this one is potential energy. This pressure over density will be the energy that a flowing fluid is carrying into the equation. Okay. I don't want to tell you more because we call that theta, but later in chapter number 5, I'm going to pretty much teach you what theta is and how we get this guy. Okay, but I just want to define and give you the definitions. Mechanical energy change of a fluid during a compressible flow per unit mass will be equals to pretty much delta E, which is equals to P2 minus P1 over density, V2 to the square minus V1 to the square over 2, and then G that multiplies Z to Z2 and Z1. Okay? I just want you to remember something that I just said a few slides ago, and this is the thing. We don't care about the energy as a whole. Okay? We care about how the energy changed from state 1 to state 2. Okay? So pretty much we calculate the change of the energy. That's why this guy right here has 1 and 2. P2 minus B1, B2 minus B1, G that multiplies Z2 and Z1. For now, you don't have to worry about that. I'm just trying to explain exactly what you're supposed to be reading of the book. Okay? That's why you have 2 and 1. So, moving to the next section in the book, we have heat and work, and we need to define them as we move in the chapter. Guys, I know I'm a little bit, I could sound like annoying because I'm telling you, read the book, read the book, read the book, read the book, but I know exactly what I'm saying, okay? I'm pretty sure if you read the book and then you watch my presentations and then you watch the videos I posted on Blackboard, everything will make sense. And if it doesn't make sense at first, it'll make sense at the second time. Believe me, it'll be like that, okay? All right, heat. The form of energy that is transferred between two systems or a system and its surroundings by virtue of a temperature difference. Energy can cross the boundaries of a closed system in the form of heat and work. Temperature difference is a driving force for heat transfer. Okay, so like I said, heat, pretty much what happened with the heat? Heat is a form of energy that will be generated by a temperature difference. Okay, so you have some temperatures in the outside and you have some temperatures in the inside. The heat is crossing the boundaries of a system. So recalling chapter number 1, we had systems and then we have some boundaries and then we have surroundings. Remember? So that's the system boundary right here, and then we have the surroundings in the outside, and then we have our system. Okay? Let's take a look at this example with the soda. Pretty much you have a room air of 25 Celsius. Okay? And you have 3 sodas. One, it's at 25 Celsius, the other one is at 15, and the other one is at 5. and the room temperature it's 25. Sorry, will travel, okay, from one point to another. If we have the same two temperatures like this one, right? This guy and the same temperature with the room here, there's no heat transfer, right? They have the same temperature. So what happened if now I have pretty much 15 Celsius right here and 25 Celsius? So pretty much the heat will travel from the high source of temperature to the low source of temperature. So it's traveling, 25 is more than 15, so it's traveling to the inside, sorry, it's traveling to the inside of the can. Okay, so heat is traveling in this way, as you can see right here, and it goes from 25 to 15. And then by the temperature difference, I'm going to be able to calculate what that heat is equals to. What I don't want you to focus on this number right now. Okay, don't focus on this. Just focus on how the heat is traveling from the high temperature source to the low temperature source. So I have this one with 5 Celsius and this one is at 25. So now some heat, like I said, don't worry about the number, is traveling to the soda. Okay, and it's making my soda to be a little bit hotter. Okay, so the temperature will increase after some seconds. But again, I don't want you to worry about that. So temperature difference is the driving force for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. And just save that right here, okay? Later, we'll understand a little bit more. So if I take a look at this example right here, you have a closed system, right? And you have your system boundaries, heat and work can cross the system boundaries, okay? In and out. And that's how you generate heat or work. Do you remember, guys, that earlier before I told you that energy it's equals to capital E, and energy per unit mass it's equals to the little e, and energy flow rate it's equals to E dot. I want you to remember that because with heat it's exactly the same thing. Heat transfer is denoted by Q. Heat transfer per unit mass is a little q, and the heat transfer rate will be Q dot. Okay, I'm just giving you information like I said. You're gonna see exactly what I mean once we get into the analysis of the system. So if you have the baked potato, right, you're gonna have that. You have the baked potato, you have the surrounding air, you have the system boundaries of the potato, and pretty much energy is recognized as the heat transfer only. You know, it's recognized as heat transfer only as it crosses the system boundaries. You're gonna have a surroundings with some temperature, and you're gonna have a temperature of the potato. The difference of those temperatures in times equals 1, 2, 3, or 4, whatever that is, will give you the heat transfer. Okay, very important. I hope there's no questions. Like I said, guys, there are a lot of videos posted in this section. I want you to watch the videos. I want you to read the book. Work. So work is the energy transfer associated with a force acting through a distance. A rising piston, a rotating shaft, an electric wire crossing a system boundaries are all associated with work interactions. And we're going to talk about something very important. Or before we talk about that, I just want to remember something. Work, like heat, is an energy interaction between a system and the surroundings. You need to remember that. It's a energy interaction between the systems and the system and the surroundings. As I mentioned earlier, energy can cross a boundary of a closed system in the form of heat and work. Therefore, if the energy of a system boundary of a closed system is not heat, it must be work. Work is the energy transfer associated with a force acting through a distance, like I just said, some of the examples, and it has some conventions. We don't have Q1 or Q2. We don't have work 1 or work 2. That doesn't exist. We have Q that goes from 1 to 2 and work that goes from 1 to 2. And just note something. When we were talking about pressure, we had pressure 1, we have pressure 2, we have temperature 1 or temperature 2. Okay? In the past, for work and transfer, for working heat, we only have working heat from state 1 to state 2. The formal sign convection. Okay? Heat transfer to a system and work done by a system are positive. Heat transfer from a system and work done on a system are negative. Remember when I told you that you need to read the terms and definition twice in order to understand? Let's do that. Heat transfer to a system and work done by a system are positive. Okay? Heat transfer from a system and work done on a system are negative. And this is always confusing for everybody, not only for you. It was confusing for me when I first learned thermo. It is confusing to the students that are learning thermodynamics at first. This is very confusing. But in order to make everything clearer or easier to understand, there is an alternative sign convention to use, and this is with in and out. Okay, that it's a lot easier than going with the work done by a system or heat traveling into the system or going outside the system. Okay, so we prefer to talk about in and out, in and out. Okay, Q that comes in, Q that comes out, work that goes in, and work that goes out. And this is your system. Okay, so you can also say, like I said, the previous one, a work done by the system. This system is producing some work or it's requiring some work. You don't want to worry about that. But let me give you a small example. A compressor. A compressor, right, will require electrical work in order to work. You need to plug the compressor, you need some energy. That will be work needed by the system. But if you have, for example, a turbine, right? A turbine is generating energy. Therefore, the work is given by the system. Okay? Doesn't need work, it's just given by the system. But like I said, don't worry about that sign convention. Use the one with in and out because it's going to be a lot easier to do exercises with that convention. Q in, Q out, work in, and work out. Heat and work. Both are recognized at the boundary of a system as they cross the boundaries. That is, both heat and work are boundary phenomena. Both are associated with a process, not with a state. What is that? So Q1 and Q2, they don't exist. We have Q1, 2. Work 1, work 2, they don't exist. We have work from one state to another. Unlike properties, heat and work has no meaning at a state. Well, same thing. Both are path functions. Okay, so pretty much we study how that work or heat is traveling from one state to another. That's what we study. I want to develop some forms of work, so we know the equations and how to play with them. To be quite honest with you, not to be used in this class particularly, because most of the time that work will be given in the statement of the exercises. But when you move to thermodynamics too, whether you're a mechanical or chemical engineer, engineering major, you will be developing the equations a little more. So when a potential difference in current change with time, pretty much we know that the work, electrical work, will be equal to the integral from 1 to 2 voltage times current, dt. But pretty much in thermo, we will assume that the voltage and the current will be constant, and therefore we will have these equations. So we can take b and y out of the integral, and then we get the WA or work we E, it's equals to BI dt, and then work E, it's equals to BI, delta T, and that's in kilojoules. Perfect. Moving to the next one. Mechanical form, mechanical, so we know this one, very simple. So there are two requirements for a work interaction between a system and its surroundings, and those are the two ones. There must be a force acting on the system, and the boundary must move. Okay, so work, this type of work is pretty much force times distance. Okay, when the force is not constant, then we need an integration, but most of the time we're gonna have our force in a constant matter, and this is the equation that we need. Work it's equals to force times displacement or distance. Okay, and this is equals to kilojoules. When you're moving your box from one point, this is number one, and it's moved to number two, it, the distance will be denoted as S, and the force needed to move the box from 1 to 2 that is given into the equation. Therefore, that's the work associated with the movement. Shaft work. This is, you're going to be using this one pretty much. So as you know, torque, it's equals to force times R, right? The distance. So force is equals, if we solve this for force, then we know that force is equals to the torque over the radius or the distance. So when we have the work of the shaft, we're gonna start with the same equation, work as mechanical, it's equals to force times distance. In this case, my force, it's equals to T over R, that comes from here, times distance. Okay, how do you know the distance? Take a look at this picture right here. Okay, so the distance will be calculated as 2PR, okay, times n revolutions, okay, the amount of revolutions that we have. If we put everything into the equation, we're going to have that the work done by the shaft will be equals to TR that multiplies 2 pi Rn, and that's equal very much to 2 pi nt. Okay, being t the torque, pi, the number, and n, it's pretty much calculated by the number of revolutions that you will have. Like I told you before, to be quite honest, okay, the work done by the shaft is usually given in a form of a number, and it's a lot easier, but you need to know exactly where that comes from so you can play with exercises in the future, not for thermodynamics right now, but this is the equation that we need. Spring work from physics. So when the length of the spring changes by a differential amount dx under the influence of a force F, the work done it's equals like this. So you have pretty much this spring at state number one, and then you have the same spring at state number two. So the spring it's elongated some distance, right, due to a force. So that's a force that you see right here. And then the distance will be dx. You don't know exactly how much will elongate. And you have the rest position. That will depend on you exactly to know if you can measure it, if you can establish that rest position as, you can establish the rest position as a reference point, and it could be equal 0. That is pretty much what it is. But the differential of the spring work is the same thing, force times distance. Okay, so the force of a regular spring, it's always equals to kx. Okay, being k the spring constant, and x will be the distance between the rest position and state number two. So if we plug everything into the equation, we get that. So let's put it like this. So let's work of the spring, it's equals to F times distance. Let's call it, let me just do this. Spring, it's equals to F dx. F for a spring, it's equals to kx. Now, what do we do? So I'm going to plug this into that equation. So I have differential of work, that's equals to F, which is kx dx. And now I'm going to integrate from 1 to 2. Same thing from 1 to 2. That the work of the spring, it's equals to 1.5 k that multiplies x2 to the square minus x1 to the square. And that's my equation. Okay? That equation is pretty much the displacement, the initial and final displacements given by 1 and 2 right here. Okay, and that's physics. Okay, but ultimately you need to know that spring will do some work. Okay, again, in thermal, usually that is giving us a number, and then you just plug the number into the equation, and then that'll work. But sometimes you will need to calculate this one. Like I said, this is physics, no thermal. All right, moving to the next one. Everything, guys, will come to this final definition. It's the first law of thermodynamics. We studied in the chapter number 1, the 0th law of thermodynamics, which was developed long after the first law. So the first law is its name as a conservation of energy principle, provide a sound basis for studying the relationship among all the forms of energy. Pretty much the first law states that energy can be neither created nor destroyed during a process. It can only change forms. Guys, this definition will be with you throughout your degree and your career. Okay, so this one right here, it's very important, and I'm gonna give you a hint. It's gonna be important for the exam. Okay, states that energy can be neither created nor destroyed during a process. It can only change forms. Remember that. And that will bring us to an energy balance. We have this energy balance, and it says that the net change, increase or decrease in the total energy of a system during a process is equals to the difference between the total energy entering and the total energy leaving the system during that process. And that is pretty much what you see right here. Total energy entering the system minus total energy leaving the system. It's equals to the change of the energy of the system. And that is what we need in order to calculate and develop behaviors in engineering devices. Moreover, we can have that energy that comes in minus energy that comes out. It's equals to the total energy of the system. Okay? Remember that. For everything, guys, from now moving on, it's going to be an energy balance. Everything that comes in minus everything that comes out will tell you exactly what is the change in the energy of the system. Let's see a small example. So you have the energy change of a system during a process is equal to the net work and the heat transfer between the surroundings. So you have the shaft, right, doing some work, and then you have, and then you have some Q in and Q out, okay? So at first you had an energy inside. At work, it's going into the system, right? You have the work coming in, right? That's some work in. You also have some Q coming in, have some Q coming out. If you know the equation, it's everything that comes in minus everything that comes out. It's equals to the delta of the energy of the system. So what's coming in? I have 15 kilojoules from the Q in. What else do I have in? I have 6 kilojoules from the shaft work that's coming in minus everything that comes out. What do I have? I have 3 kilojoules, and that's equals to the energy of the system. So 15 plus 6, how much it is? So I don't have a calculator, so 15 plus 6 would be equals to 21 minus 3, it's equals to 18 kilojoules. Sounds simple, and for some people might be a little bit uh, too simple, but that's the key of everything, okay? Everything that comes in minus everything that comes out, it's equals to the change of the energy of the system. So energy change of a system, okay, also could be defined with a state. The energy change could be equals to the energy at the final state and the energy at the initial state, if you want to use the previous conversion, right? Like the work that is done and everything. Okay, just remember that delta E, it's always equals to delta U, or let's put it like this. E, it's equals to internal energy plus kinetic energy plus potential energy. But I don't care about E, I care about delta E. So delta E will be equals to delta U plus delta KE plus delta PE. And PE, internal energy, KE, and PE are right here. And you always need to calculate that. But let me tell you a little secret. Most of the time, the change in kinetic energy and potential energy are almost neglectable for exercises. Okay, sometimes this guy will be zero, this guy will be zero, and then you will have only to deal with the change of internal energy. But that's coming later. Okay? Now, as for a system undergoing to any kind of process could be developed like this. Energy that comes in minus energy that comes out, it's equals to delta energy of the system. Okay, and I'm just being a little bit annoying because I'm repeating the same thing always in a rate form. Could be also delta energy, the energy rate coming in minus the energy rate coming out, it's equals to how the energy of the system will change respect to the time. Okay, so this guy right here, it's the rate of net energy transfer. Okay, and this guy, it's a rate potential energies, or etc. I'm just gonna call all forms of energy. Okay, just remember that it's very important. So mechanism of energy transfer, I'm just rewrapping everything. It's pretty much heat transfer, work transfer, and mass flow. That's coming later, okay? This one right here. For now, we just need to worry about heat transfer and work transfer. Mass flow rate is coming later. A closed system mass involve only heat transfer and work because that's what we're focusing right now. Okay, so that guy, the mass energy, the energy that the mass is carrying will be probably neglectable for now, and we're gonna just save it for later chapters. But for now, we need to worry about heat and work transfer, and this is the equation for most of the things. Okay, so the energy content of a control volume can be changed by mass flow as well by heat and work interactions. Okay, you're gonna have mass coming into your system and you're gonna have mass coming out of your system, and these interactions will generate work and heat. Those three things are gonna be always related, which is one, this is also one, and then two and three. Okay, that's how we study our engineering devices. Efficiency, okay, everybody knows probably what efficiency means because you've been working with that in other classes. So efficiency is one of the most frequently used terms in thermodynamics, and it indicates how well an energy conversion or transfer process is accomplished. Efficiency is equals to the desired output over the required output. Okay, so you have something like, let's say, compressor, right? The compressor will essentially will deliver some work, right, or some energy, and that energy should be equals to X number. The compressor will require some work in order to deliver that energy, and the difference between those two will tell you how efficient is your device. And that's pretty much important, because when you have it's very important because when you have your engineering devices, you need to know exactly how much energy you actually need to produce another amount of energy, okay, or how much energy it's pretty much delivering over the amount of energy that your system is requiring. Okay, so that's why you always are going to have a desired input and a required input. Let's say you're designing for a system, and then you do your calculations, and turns out that you need a machine that is able to give you, I don't know, 1,000 kilojoules of energy. Okay, first of all, what do you do as designers? You will find the machine that you need. Once you know whether it's a turbine or something like that, okay, then you need to go into the catalogs for turbines, and you need the ones that will produce that amount of energy. That will be attached with something that is required in order to run the machine. So both of them combined will tell you how efficient your system will be. And therefore, when you are presenting your work to somebody else, you can say, I have a generator that is efficient as much as, I don't know, 90, 80%, things like that. Efficiency will be pretty much given in the next chapters, chapter number 5, when we start developing the different engineering devices that we have in the industry. For example, the efficiency of a water heater is the ratio of the energy delivered to the house by hot water to the energy supplied by the water heater. Again, you need some amount of hot water coming to your house, but you also need some energy that will make you produce that heat water that you need. Okay, that hot water that you need, sorry. Efficiency of mechanical and electrical devices. So pretty much it's the same equation that we had before, but now we're going to add the mechanical work. So mechanical efficiency is equals as the mechanical energy output over the mechanical energy input. Okay, or if you want to see it as this one, is the desired output over the required output. It's exactly the same thing. Some mechanical energy that I need to be generated versus the mechanical energy that your system will need. The efficiency, the effectiveness of a conversion process between the mechanical work supply or extracted and the mechanical energy of the fluid is expressed by the pump efficiency and turbine efficiencies. Okay, we always use that. And why is that? Because the pump will actually be the opposite of the turbine. The turbine will use the water going into the turbine to generate some energy. The pump will require some energy in order to give energy to that fluid. Okay, and this is giving it has, sorry for this presentation, these guys right here are not right. So in terms of the mechanical of the efficiency for a pump, right, I will have the efficiency, sorry, let me just go like this. So efficiency of a pump will be equals to pretty much delta E of the mechanical fluid over the work required by the shaft. Okay, in other words, it's pretty much the work that the pump is producing. Remember, always desired input or output over the required input, okay, which is the work that the pump needs Okay, so this one is the work of the pump that is delivering into your system over the work that is required by the shaft in order to work. With the turbine, it's similar. So efficiency of the turbine, okay, it's equals to the mechanical energy output, which is the work of the shaft, over the mechanical energy decrease of the fluid, which is the delta of the energy of the mechanical fluid. And this is not more than the work given by the turbine, which is expressing energy, and the mechanical energy of the turbine as well. This is different now because now this is coming in and this is coming out. Okay? So just remember that because it's very important. And we always use the turbine and the pump because they're different from one another. So the pump will actually give energy to the fluid, and the turbine will use the energy of the fluid in order to generate electricity. Okay? So, like I said, pretty much they will come from the same equation. And what equation is that? Efficiency, it's equals to the desired output over required input. Okay? That equation will work for all efficiencies, guys. Not only for pump or turbine, for sure. Once we understand what the pumps are, or how the turbine will work, then we can establish which one is desired and which one is required. Okay? Something important, and again, in the book that will be explained in this chapter, but this is just, like I said, an introduction. Okay, and it's when you have two components connected, right? And you need to know exactly how much is the efficiency of the whole system turbine generator. You're gonna have an efficiency for your turbine and efficiency for your generator. Okay, the efficiency of the whole system as a system will be the multiplication of the efficiency of the turbine times the generator. So 0.75 from this one and 0.97 will give me a total efficiency of 0.73. This topic will be developed in chapter number 5. So if you didn't understand exactly, or you didn't have the idea of the efficiencies right now, that's fine, guys, because we're going to develop those once we reach chapter number 5. Okay, we're still developing equations, we're still developing terms and definitions. Okay, so with that, that's the end of chapter number 2. Again, there's more information in the book, there's more information in my notes. So now you have my notes, you have the presentation, you have the book, and you have homework to be done. Okay, well, guys, that's all for today. Thank you very much for your time, and I hope these will help you.